record that video on this topic, railway noise retrofit mitigations. In the video, Richard Grant and Professor Lam Kinji will talk about this railway noise retrofit mitigations. Before we play the video, I would like to have a quick review on the background information, specifically on this 5 area, the railway noise mitigations from the EIA perspective or from the retrofit perspective. They have different view angle. And then talking about the last 20 years, the airborne railway noise is actually increased due to the implementation of the ground-borne noise control mitigation, because they use resilient baseplate to improve the ground-borne noise. However, it increased the airborne noise. Then we talk about some relationship between the railway vibration and the rolling noise. Actually, rolling noise is 95% coming from the rail vibration in most cases. So once we can reduce the rail vibration, then rolling noise would be significantly reduced. Then talk about this international standard, the TSI noise limit. This noise limit is talking about for all the rail train from the European country or even from China, they would achieve this limit. This limit is when they traveling at 80 kph at ballast track, if we measure the noise level, it should be less than 80 dBA. So we will talk about this. Then we will talk about the rail damper noise reduction performance in this different situation. Then talk about the principle of noise control. It either control the noise source or noise reduction at the transmission path or sound insulation at the receivers. Based on these 3 principles, there is a lot of different noise mitigation measures are considered and developed during the project planning stage. All the new railway project, they will consider every aspect to reduce the noise. And also there is a EIA. The EIA would normally focus on the mitigation in the transmission path, such as how much noise barrier or the receiver insulation, such as the acoustic window or acoustic balcony to reduce the noise impact to the residents. Because they assume that the noise reduction at source is already conducted at its best practicable design based on the project constraint. In many cases, we still find there is noise camping, even though the EIA meets all the desired noise standards. Noise mitigation measures for the transmission path and receiver are difficult to implement after the train service. If we still receive noise camping after the train service, we need to consider the retrofit mitigations. So then we come back to whether we can control the noise source. The question is, what source are available for retrofit mitigations? So then we look at there are different railway noise source type. There is rolling noise, normally is the major noise source component. It is coming from the vibration of the rails, normally is the vertical vibration. Then squeal noise. Squeal noise is only occur at the curve track. It may not occur because if we have a very good design, then squeal noise may not occur. So then also at impact noise. Impact noise is talking about when the wheel traveling across a rail gap in the joint or in the crossings. Traction noise refers to all the traction motor noise or all the undercar equipment. Aerodynamic noise refers to the air molecule movement around the train body. That is not important until it's very, very fast. Then the vibrated noise and the ground-borne noise. These 2 have been reduced significantly in the last 20 years. So among all these 7 different types of noise source, rolling noise are most important because around 95% of the noise is coming from the rolling noise, from the rail vibration. So once we control the vibration of rail, it should reduce the noise significantly. It is noisier than other source by 5 dB to 15 dB. In the last 20 years, due to the vibration control, ground-borne noise control, resilient baseplate have been commonly used in all the new railway. With the resilient baseplate, the vibration energy are separate from the structure. So the rail vibration energy will be kept within the railway, not allowed to transmit into the structure. Once they keep in the railway and there is multiple rail excitation, the vibration of the railway vibration would be accumulated to making the rail vibrate more seriously, much higher amplitude, and making the rolling noise become further increased. So the reduction of the ground-borne noise is actually increase the rolling noise. Okay, let's look at this picture. This picture is last time we already discussed in the last webinar. It shows the noise source, the noise level at different train speed, which also presented in the last webinar. The y-axis on the left side, is the noise level measured at 7.5 meter, the spontaneous noise level. The x-axis is the speed of the train. For example, if we are talking about 80 kph measured at a ballast track and measured at 7.5 meter, the TSI limit is 80. In Hong Kong, of course, we are better than the TSI limit. So in this case, the measured noise level is around 79. This is the red line. The blue line is the rolling noise coming from the wheel vibration. The green line is the traction motor, the traction noise coming from all the undercar noise. So if we can control the wheel vibration, this blue line can be reduced a lot, such that the noise level, attributed noise level, would be around 71 to 75. So that if we can have good control on the wheel vibration, we can achieve 71 to 75 dB, 5 to 9 dB better than the TSI limit. However, in the last 20 years, to control the ground-borne noise, we use the resilient base plate. The resilient base plate actually isolates the vibration from the wheel to the structure, such that more energy stay in the wheel, making the wheel become vibration at higher magnitude, making the entire wheel become noisier. And this increased noise showed as a dotted blue line, and the overall noise is the dotted red line. If talking about traveling at 80 kph, it is 85 dBA. So in this case, if we can have a good damper to control the wheel vibration, we can still going back to this level, 72, 73, or 75 dB. So in the case with resilient base plate, because the rolling noise is elevated, such that the TSI noise limit, TSI measurement method would give 85. Once we use a wheel damper, we can control it back to 75 or 73, so that the noise reduction by wheel damper would be 10 or even 12 dB. It should be noted that the scale on the left side and the right side are different scale, because on the right side, this is the average noise level over half an hour. Although the train travel faster, it make the noise, but the traveling time is shorter. So this making these two assets become different. This was explained in the last webinar. Okay, then talking about the TSI noise limit. In the past, the railway are directly fixed on the ground, fixed on the structure. So they are very hard. Okay, let's look at this graph. The y-axis is the airborne noise at 80 kph at 7.5 meter. Measured as 7.5 meter. The x-axis is the how soft of the base plate or the support the wheel pad, how soft the wheel pad. If the wheel pad is very deep, very stiff, then the noise level would be lower. If the wheel pad is very soft, the noise level would be higher. So this is talking about the noise level at different fastener stiffness. In the past, the wheel pad is very stiff, so the noise level is 79, 78, better than the TSI limit. Then for ballast track, it could be 60 to 200, the wheel pad stiffness. So the noise level a little bit increased to maybe 82. And then in nowadays, they use one other resilient base plate, egg or floating slab. Then the noise level will increase 85, maybe even 90. If they are using very soft fastener. So the noise level is increased by using different fastener. If they want to have a better ground-borne noise control using a very soft track support, such as this case, then the noise level, the airborne noise level will be increased by 10 dB. If we put a wheel damper, they always around 72, 73. So if we only have 1/4 insulation, then it would be this line would be 77. 1/4. If half installation, it would already around 75. If every space installed with the wheel damper, it would be 73. So how much noise reduction by the wheel damper is really depending on originally how much noise coming from the wheel track. In the ballast track, it only reduces 3 or 4 dB. In the resilient base plate floating slab track, it can easily achieve 10 or 12 dB noise reduction by wheel damper. Okay, this is the noise reduction by wheel damper predicted. So it really depending on which type of fastener are using. If it is very soft, the expected noise reduction would be very high, around 10 dB, 8 dB. Okay, this is come to the end of my overview on the background information. We are going to play a video, pre-recorded video on this LMS. Before the Q&A session, I would like to further explain the 1 or 2 items. Would you let me share my screen? Okay, this was shown in the video. The wheel vibrations without damper is very high. Once we put our damper, all the vibration energy will transmit into this oscillator. This oscillator is 90-degree phase led to the railway vibration, such that it always creates a counteractive force to the rail vibration. And the amplitude of the oscillator is normally 5 to 8 times higher than the rail vibration. So it creates a very, very, very high counteractive force to suppress the rail vibration. With this amplified movement of the oscillator, all the energy are dissipated in rubber layer. So this is the design is totally different from all the other wheel damper design, because other wheel damper design, they use a rubber layer at the interface, and they try to maximize their interface area with the wheel. We minimize we have a metal to metal contact interface such that has very rigid contact all the vibration energy will be transmitted into the whale. And with this rubber layer at the flat surface, we can very easy control, effective control the stiffness. And in terms of the rubber layer to dissipate energy, we have the area is very large. We have this area, and every surface have this area. Altogether, if we have multiple damper, then the area is actually more than the whale surface area. And we have higher vibration amplitude to dissipate the energy. So this is why the Q damper is different from other, because they do not have a rubber interface at the interface between the whale. So this is the first point I would like to further explain. The second point I would like to further explain, talking about the rotational grinding. Normally, after the rotational grinding, they have this grinding mark. This grinding mark would make the whale have a roughness. For example, like this, typically would be 5 to 10 dB higher than the TSI limit at the very small wavelength, 10 millimeter, a millimeter, this type of wavelength. And this type of roughness, it is actually 1 micrometer. This is talking about 1 to 1,000 millimeter, 1 micrometer. However, it's already very high, 8 dB higher than the TSI limit. But with the 1 or 2 month string operation, the wheel would smooth the whale surface. So this looks very high, but actually, once the whale operates, this will be smooth very quickly. So this is 2 more items I just explained, and I will hand over to Max for the Q&A section or other introduction on the coming webinars. So Max, I hand over for the Q&A section for you. Is there any questions?
So this is our upcoming webinar. The next webinar is going to be held on March the 8th, and the title is EIA Railway Airborne Noise Prediction Uncertainty. We will issue some invitation 2 weeks before the webinar, so stay tuned, everyone. So now is the Q&A session. Please feel free to ask any questions, and we will answer your question.
Okay, I saw the first question. I'm not totally understand. The airborne noise emitted from the whale seat on the resilient pad will increase the airborne noise. Will the Q damper have a better noise reduction performance for whale on resilient pad than the stiff pad? Yes. Max, would you allow me to share my screen? Okay, maybe I did not well explain. Okay, how much noise from the whale wave vibration is depending on how much isolation from the structure. If they use a very soft whale pad, then they are more isolated from the structure and more vibration energy stay in the railway, making it more airborne noise weighted there. If once use the whale damper, we can always reduce the whale vibrations, the airborne noise from whale vibration to this type of level. So it really depending on, for example, if this is 10 kilonewton per millimeter, if the whale pad is 10 kilonewton per millimeter, that is a very soft, resilient base plate, then the noise reduction would be expect around 15 dB. In Hong Kong, they are using this egg or the ATP egg or the Sydney egg. They are around this level, so the reduction would be around 10 to 12 dB. If a full installation of the whale damper, it would reduce 10 to 12 dB in the Mox whale and the West whale. So this is depending on which type whale. But in East whale, because most of them are ballast trap, so the noise reduction would be 3 or 4 dB, or depending on how steep of the pad. So this, I hope I answer the first question. Max, could you read the question for me?
Yes. The second question is from Wong King Yuan. Hi, Wilson. What makes people still complain even with barriers?
Okay, there is, I think, a lot of reasons. Some people are more sensitive to noise. Some people have a higher expectation, even all this statutory requirement are satisfied. They expect a better environment. For example, if the environment is very quiet before the new project, then it come to once the railway line bypass its house, it already very quiet. But compared to the before the project, they still increase 10 or 15 dB. So then they will complain. I remember when the new airport operates, a lot of complaint from Chengyi, from Satin. Why they complain the aircraft noise? Actually, they're very quiet. The aircraft bypass Satin and bypass Chengyi is not very noise. But most of complaint was from the Satin and Chengyi due to the new airport operation at Chet Lap Kok, because they they did not expect the airport would create such noise, although the noise level is very quiet. So I hope this may be one of the answer. So another.
What is the lifespan or durability like for the rubber damping material within the Q damper?
We always try to choose a long life material. According to the material specification, it should have 20-year lifetime or more than 20-year lifetime. In our design, because the rubber is actually sandwiched by the stainless steel, so the only surface exposed to air is the edge, 1 millimeter thick edge at the circular edge. So if there is any oxidation or ultraviolet hardening, it only at the surface. So we believe it can last for 20 years or more than 20 years. So we first installed the damper at 2010, and we removed the damper. Some of damper have been removed, and we checked the rubber properties. There is no change in the rubber properties in 10 years. But we don't know how it would be. So, and the next question is,
does Q damper have the same damping effect on horizontal and vertical vibrations? Is it possible to make vertical damping effect even higher?
At the moment, the vertical and lateral vibration damping are same. This is why our damper are able to reduce corrugation and others does not show similar ability, because corrugation is majorly coming from the lateral vibration, lateral wheel resonance. And the wheel damper is all the other wheel damper, they are optimized for vertical vibration control. They are optimized for vertical wave because their rubber orientations, they need to either choose optimize for vertical vibration or optimize for lateral vibration. And vertical vibration is the airborne noise major component, so they are optimized for vertical vibration dissipation. However, our damper is vertical and lateral have same effect, so that the first damper installed in the Kwun Tong line at Jungle line in 2010, it is unexpected that the corrugation have been suppressed. So we did not expect have such in the first installation, we already have the corrugation suppression. So this is due to the vibration absorption at the lateral direction. And is it possible to make vertical damping even higher than the lateral? Yes, we have different design to make the, actually it's not higher. We try to make, they have different resonance frequency. Because this is a tune mask damping, we can tune it for 500 Hertz, for 1000 Hertz, or 200 Hertz, or 50 Hertz. So normally the vertical vibration would be around 800 to 1000 Hertz. If for control of the vertical vibration, the tune mask damper should be tuned to 800 to 1000 Hertz. If for lateral vibration, normally we would tuning for 300 to 500 Hertz. So depending on which vibration we want to control. If for ground-borne noise, we would tune for 50 Hertz or 60 Hertz. Okay, look at the next question.
There's two questions. How rail surface roughness related to rail noise? Will it get more rough over time?
Rail roughness is can be generated by two mechanisms. One is from the rail grindings, the other is from the operation. Talking about the rail grindings, in the old days, they used the rotational grinding stone. And when the rotational grinding stone with the linear velocity of moving of the grinder, they would create a grinding mark at 10 or 15 millimeter gap. A regular grinding mark. Such regular grinding mark would create a distinct tonal noise at maybe 800 Hertz or high frequency. And this grinding mark, however, in Hong Kong, we already use a very, very good grinding machines. And some of them, they use a milling or longitudinal grinding. They are totally remove this grinding issue. If there is MTR people, they have they can supplement on the grinding. I think they have more information on how to control the grindings. Okay, on the other hand, on the roughness is when the wheel running on the wheel, it would increase the roughness. It is, in general, it would be randomly increase. So it could be wavelength 10 millimeter, 20 millimeter, 25 millimeter. However, due to certain resonance or a curve track, there is some kind of string reaction, they would create a regular pattern. This we call the short pitch corrugation. In curve track, it would be around 30 millimeter, 40 millimeter. Such short pitch corrugation would increase very quickly. Okay, I made refer to some of the slides regarding this. Let me find out the slides. Okay, are you able to see the PowerPoint? This picture was presented in last webinar. We talked about in the Eurotime project, we take two roughness measurements. This measurement is just 2 weeks because we try to make a very, very good surface, making a very good small surface. The dotted line is the very good surface. It is 5 or almost 10 dB better than the TSI limit. TSI limit is very difficult to achieve. It is better than the TSI limit. So then we measure it 2 weeks later, and we found that the roughness increased. And if you, let's see it, this is the noise level we measure at the same location. We know that when the railway let it run for half year, the roughness will go, the noise level will go like this. And this noise level, tonal noise at 630 is due to the rail corrugation. This rail corrugation is equivalent to 32 millimeter wavelength. 32 millimeter wavelength is this. So in 2 weeks, the roughness increased by the rail operation is from 0.3 micrometer to 0.42 micrometer. That within 2 weeks, the roughness increased 0.12 micrometer. So if we continue to every 2 weeks increase 0.12 microns, every month it will increase 2.5 microns. Let me see it. Okay. So for half year, with the corrugation growth of 0.25 micron per month, it will go to this. This is based on the linear growing of the corrugation. All our data showing the corrugation growth are linear. So they grow at 0.25 micron per month. But many other researchers suggest that the corrugation growth is exponential growth. So they grow at 6.1 dB per month. So after half year, it growth increased 36 dB. So at the moment, most research thinks that the corrugation growth is exponential. Our data showing it is linear. So, but we are not going to do extensive research on corrugation growth. So, but anyway, we are talking about within half year, the roughness will go from there to there. So it would increase the noise level by 10 dB, around 10 dB in half year. Okay, any more questions?
Yes. Next question is, in your slide showing the soft rail fasteners generate more vibration and higher noise than the pendrol fasteners, say, would it be better to use pendrol fasteners than the expensive rubber fasteners to save fasteners cost?
Oh, sorry. Because the question is complicated, I want to look at, is it from which one? Last one, the 719?
Yes.
719. Okay, informative in your slide showing the soft rail fastener generate more vibrations than, and actually the soft rail fastener has less vibration transmitted into the ground, but the rail have high vibration. So in terms of ground-borne noise control, soft fastener is much better. But in terms of airborne noise, soft fastener will lead to higher airborne noise. Okay, the question is, would it be better to use pendrol fastener than the expensive rubber fastener to save the fastener cost? Yes, pendrol is very good at fastener. I think this question is yes. Pendrol have different, the whole different stiffness fastener. The very soft, as soft as 5 or 6 kilonewton per millimeter, or very stiff, 100 kilonewton per millimeter. They have entire whole series for different applications, and their keep is very good. So I saw many cases they try to replace pendrol with other fastener or what other clips. They generate a lot of problem. But so your question is yes. So any other questions? Or if somebody would like to ask the question through the Rebel is also welcome. I want to keep the webinar within 1 hour. So if we are still waiting for the questions, I have prepared that in the slide, we also, in the video, we also talking about the noise barrier and the rail damper, the noise reduction. I want to further explain on this. The noise barrier can reduce very good noise reduction, 15 dBA or even 20 dBA reduction at the lower floor, and at the middle floor maybe 10 dB reduction. But once at the upper floor, outside the shadow zones, there is no noise reduction. So this is the problem of noise barrier. It has better to be a noise enclosure or a canopy. But to do a noise enclosure canopy would the wind loading would make a very challenge for the structural design of the bridge. So if for using the whale damper, because the noise reduction is from the source, so it could be minus 10 dB or minus 5 dB, but the benefit is for the entire building. So the best design would be a noise barrier for the lower floor, then the damper for the upper floor, then all the entire building, lower floor and upper floor, are totally protected. Okay, so are there any more questions? Winston, will there be difference in noise reduction for track with wooden or concrete sleeper? Yes, but this is complicated because how much vibration isolation is depending on the wheel pad and the sleeper. Wooden sleeper, I'm not sure. Could somebody help me? I'm not sure if using wooden sleeper, what type of wheel pad would be under the wheel. For the concrete sleeper, because they use a very steep wheel pad, normally is a few hundred kilonewton per millimeter. So the vibration would be easily transmitted to the sleeper, and a lot of energy would be dissipated in the sleepers. So I think a ballast track with concrete sleeper is already required because they use a slip wheel pad and the vibration transmit into the sleeper, and the sleeper at the ballast track have some friction to dissipate the energy. For the wooden sleeper, I'm not sure what is the wheel pad stiffness. Anyway, the wooden sleeper is less massive, so the energy dissipation would be less, and also maybe it is softer. So I have no idea on the wheel pad stiffness on the wooden fastener, wooden sleeper. But concrete sleeper at ballast track would be very quiet. Okay. Hope you can join the next webinar. I forgot the title of the next webinar. Master, would you show what would be the next webinar? Actually, I trying to develop a noise calculator for the how much noise reduction by whale damper. So I want to have an online calculator. Everybody allowed to input their site information to find out how much noise reduction and in their sites if whale damper, effective whale damper are installed on their site. So I'm going to make this within this year. I hope I can make it online calculator. And for a very simple idea, if in your site the noise level sometimes is 56, sometimes is 61. So it, for example, it between 56 and 61. Then once install the whale damper, it would be less than 54. So because install the whale damper would normally making the whale quieter than the quietless moment. So if originally your whale noise is between 56 to 61, once install the whale damper, it would be 54 to maybe 53 to 55, the noise level from the whale. So this is one simple step to estimate how much noise reduction by installing with effective whale damper. Okay, I did not see more questions. The next seminar would be the EIA Airborne Noise Prediction Uncertainty. Actually, the EIA prediction method has a lot of safety factors, so those uncertainty would not affect the noise result. Only at the curve track. At the curve track, there is a lot of uncertain dynamic mechanism, making the prediction is very difficult. So in the next webinar, I would try to talk something about the uncertainty in the curve track. So thank you for your joining this seminar.